I now call to order the Society's 2,384th meeting in the 146th year since its founding in 1871. Good evening, everyone.
Good evening.
My name is Larry Milstein. I am the president of PSW, the oldest scientific society of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests, including those who may be tuning into our live stream, to tonight's lecture by Nima Arkani-Hamed in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C. We'll begin with a few announcements, including the results of the annual election of officers. This will be followed by a reading of the minutes of the 2,383rd meeting. We will then turn to this evening's lecture, followed by a question and answer period. Thereafter, I will present a small thank you gift to our speaker, make a few closing announcements, and then adjourn the meeting to the social hour. Please join me in thanking the sponsors of the Fall 2017 and the Spring 2018 lecture series, the Policy Studies Organization in cooperation with the American Public University, and a generous sponsor who is asked to remain anonymous. We have some luminaries of PSO with us tonight, so if we would all please give Paul Rich and Daniel Gutierrez a nice round of applause for their support. And I think those of us who attended the DuPont Summit also thank PSO and the folks over there for affording a free registration to PSW members to attend that all-day conference. I am pleased to announce that tonight's speaker, Nima, has been elected to membership in the Society. Let's please welcome him to membership in PSW. If, in addition to Nima, any of our recently announced new members are here tonight and did not pick up their signed reprint of Volume 1 of the PSW Bulletin, please see me after the lecture, and I will be glad to give you the copy. This year, there were 4 offices up for election. Upon recommendation of the nominating committee, the General Committee proposed 4 candidates to fill the openings, and ballots were sent out to all dues paid and life members, proposing the nominees for election by the membership and providing options to write in other candidates for all 4 offices. Voting closed yesterday and the results were tallied. All of the candidates were elected unanimously. There was, however, one ballot voting only for the candidate for treasurer, unaccountably, and another ballot having, instead of a vote for Anne McQueen as member at large, a write-in that was write-in. So, otherwise, the election of officers was by unanimous vote of the voting membership. And please join me in welcoming, well, not me, but Vice President Mark Clampin, who couldn't be here tonight, Treasurer Brett Magaram, and member at large Anne McQueen. If they're here and they stand up, please give them a round of applause and thank them. Their willingness to work on behalf of PSW is really greatly appreciated. As you can see, we've already put Brett to work streaming and Ann to work doing the social media aspect of our streaming program. And we now turn to tonight's lecture. Oh, no, we have to have the reading of the minutes. Sorry. We will now have a reading of the minutes of the previous lecture by our recording secretary, James Hewlin.
Thanks, Larry.
Oh, and I did forget one thing that's really important. I'd like to thank outgoing Vice President Lloyd Mitchell and outgoing Treasurer John Ingersoll for their service to the Society. So please, let's all have a nice round of applause. James.
Thanks, Larry. Good evening, everyone. At the Cosmos Club in Washington, D.C. on November 17th, 2017, President Larry Milstein called the 2,383rd meeting of the Society to order at 8:06 p.m. President Milstein announced the order of business, announced the evening's lecture would be live-streamed on the internet, and welcomed new members. The minutes of the previous meeting were read and approved. President Milstein then introduced the speaker for the evening, Gerald Joyce, professor at the Salk Institute. His lecture was titled, Life 2.0, Synthetic, Self-Replicating, and Evolvable Systems. Looking at life here on Earth, Dr. Joyce's research asks, where did it come from? How did it work? And can we make another one? In other words, can we make a life 2.0? Our planet developed 4.5 billion years ago through a process called orbital gardening, and it was initially a violent, uninhabitable place. Around 4.2 billion years ago, a hydrosphere developed. Prebiotic chemistry then took place, and many scientists believe around 3.8 billion years ago, the first life came into being. Joyce said this life was based on RNA genetic material, and this RNA life gave birth to the first DNA life around 200 million years later. Joyce said, we are the dust of the RNA world, and we can see remnants of that world in our own biology. To wit, our cell ribosomes are RNA machines. They are RNA enzymes that catalyze their own replication, remaking themselves. Many scientists believe that an RNA enzyme was the origin of RNA life on Earth. RNA molecules are strings of letters, similar to DNA. These strings are molecules that, by virtue of the sequence of the letters, fold into a shape. Some shapes are able to catalyze the self-synthesis of the original RNA string. To learn about how life began on our planet, Joyce said, we need to either dig one up of these original RNA enzymes, find such an enzyme working in modern life, or make one. Well, RNA deteriorates quickly, so finding an original replicator molecule in the ground is unlikely. And no one has identified such a molecule in living biology. So, Joyce said, he and his team have set out to create an RNA self-replicator in the laboratory. To create the replicator, Joyce's team started with short RNA strings, mutated them in a test tube, and selected those that could recreate themselves, carrying out a kind of Darwinian evolution in the test tube. Joyce described the process in considerable detail, showing numerous replicators that act by themselves and some that act in tandem with one another. Joyce and his team have since spent almost 20 years evolving such molecules to create enzymes that can replicate longer and longer strings of RNA. They also discovered that some of their RNA enzymes can replicate other RNA enzymes, even though they are limited in their self-replicating ability. Joyce also described a variety of approaches to improving and expanding the replicative abilities of these enzymes. He concluded by saying that he was looking forward to exploring how RNA could have led to DNA. President Milstein then invited questions from the audience. One member asked Joyce if he believes there was a double-stranded RNA intermediary on the way to DNA. Joyce said it was possible, but that it was also possible there was no intermediate. There are examples of such evolution in known viruses, although he acknowledged viruses are not perfect analogs because they require a host to replicate. Another member asked where the energy came from to drive the replication. Joyce said the system was not in equilibrium and is being fed by the individual building blocks of the RNA. The chemical reaction of joining building blocks to one another is energetically favorable in the joining direction and actually releases energy, about 10 kcal per mole per bond, driving the reaction forward. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 9:46 p.m., President Milstein adjourned the 2,383rd meeting of the society to the social hour. Temperature, 6°C. Weather, mostly clear. Attendance, 109. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. Are there any corrections or comments on the minutes? If there are none, I will entertain a motion from a member to accept the minutes as read. Thank you, Robin. Do we have a second? Al? Thank you, Al. All those in favor of approving the minutes as read, please raise your hand or say aye. Aye. All members opposed, say nay. The minutes are unanimously approved as read and will be posted to the website in due course. May I recommend to you that if you're interested in the subject, you really should watch the video for all of the structures that were presented and the more detailed explanation of how these molecules work and how they've been evolved in the test tube. It's really quite an interesting subject. And with that, we'll turn to tonight's lecture, and it's my pleasure to introduce tonight's speaker, Nima Arkani-Hamed. Nima is professor at the Institute for Advanced Study in Princeton and concurrently is A.D. White Professor at Large at Cornell University. Nima is one of the leading theoretical physicists working today. His interests include high-energy physics, string theory, cosmology, and collider physics. He's made a number of fundamental contributions to modern theoretical physics, among other notable contributions, including his doctoral work on supersymmetry and flavor physics. Nima worked out theories of fundamental physics involving large extra dimensions in collaboration with his friend and fellow physicist Savas Dimopoulos. Developed fundamental physical theories involving emergent extra dimensions, referred to as dimensional deconstruction, and developed little Higgs theory, working with Howard Georgii and Andrew Cohn. Before coming to the Institute for Advanced Study, Nima was professor of physics at Harvard. He was on the faculty at UC Berkeley before he went to Harvard and had been with SLAC National Accelerator Laboratory at Stanford University before joining the Berkeley faculty. He is the recipient of numerous honors and awards, not only for his work in theoretical physics, but also for his teaching. He received the Phi Beta Kappa Award for teaching excellence at Harvard, the Sackler Prize from Tel Aviv University, the Gribov Medal of the European Physical Society, and the IFN-Pisa Gambarini Prize. In addition, he is the inaugural awardee of the Fundamental Physics Prize. He is a fellow of the American Academy of Arts and Sciences. He delivered the Messenger Lectures at Cornell University and is one of the physicists featured in the award-winning documentary film, Particle Fever, made by his friend and colleague, David Kaplan, who gave a talk here in this very room almost exactly 1 year ago. Nima earned a PS in mathematics and physics at the University of Toronto and a PhD in physics at UC Berkeley. Please hold questions for the question and answer period at the end of the lecture, and join me in welcoming Nima to the podium.
All right, well, is that too loud? Is that okay? Is that okay? All right. So it's absolutely wonderful to be here in this beautiful setting. We're going to be enjoying some light after-dinner entertainment with the subject of the doom of space and time. Let me just say a few things. I shouldn't start yet?
I think we're going to trade mics.
Oh, we're going to trade mics.
Your mic sounds horrible.
All right, sorry. I may have put it on wrong. Oh, it's okay. Is that better?
That's not quite right. There we go. Let's see.
Is that okay?
Yeah, I think.
All right, fine. So let's do this. Now we're going to get it hopelessly entangled. Now we're going to see what's in my pocket. Actually, I don't want to do that. You know, cat pictures. You know that. There we go. There we go. Okay. Ha. That's why you get paid the big bucks. There we go. All right. Is that better? Okay. So first, just a few words to put things in a little bit of context. Fundamental physics is the oldest and most mature part of science, depending on where you start counting. Our field is 2,000 years old or 400 years old, really, in its more modern incarnation, starting with Kepler and Galileo and Newton. we understand the way things work really well now. Okay, our understanding of the structure of the basic physical laws of nature, especially after the revolutions of relativity and quantum mechanics in the early part of the 20th century, is absolutely spectacular. You know, 100 years ago, it's amazing that human beings could walk around on the planet and not know the answer to questions like, why is water wet and why is grass green? Okay? We have answers to all such questions now. Really, everything about the sort of basic structure of the world around us are beautifully understood in the context of these two great principles, the two great revolutionary principles of 20th century physics, quantum mechanics and relativity, which is really quantum mechanics and Einstein's picture of space and time. Now, beyond that, we do more esoteric things. You know, we want to test the way these laws work. We can make predictions for things like the magnetic properties of electrons, where we can, in some happy circumstances, we can do theoretical calculations to 12 decimal places. And our experimental friends can make an experimental measurement to 12 decimal places, and they agree to 12 decimal places. Okay, so we have this absolutely spectacular theoretical structure and understanding of the basic laws of nature. And that's why most of the developments in most of science, certainly, but also even in this part of science, should not have the character of pulling the rug out from under you, okay? Because things work amazingly well, right? And that's why only every century or so, on that kind of time scale, do you run into a situation where you suspect something very big is wrong, and indeed you do have to pull the rug out from under yourself. And something that seemed like an absolutely, completely obvious, hardwired into the way we think about the universe thing has got to go and has to be replaced in some totally shocking way by more primitive, more alien principles and ideas. That's the kind of place we are in our field today. Okay, and there's a number of different problems that I could say this about, and I'm focusing on this one that has to do with the end of space-time. There's one or two other problems of this rough character, but I'm going to split. So I'm going to try to do something very dangerous in this talk. Whenever talking about fundamental physics or theoretical physics to even a slightly general audience, and this isn't a perfectly general audience, of course, I understand, but even so, there's always a temptation to lapse into metaphor and simile in order to explain concepts that can't really be explained in that way. They have to be ultimately understood in more precise mathematical terms. That's perfectly fine. I've done it myself on more than one occasion. I'm sort of sick of doing it, though. And what I'm going to try to do in this talk is tell you, the very dangerous thing is I'm going to try to tell you true things. Okay? So everything I'm going to tell you is going to be true and accurate. Some of them will be purely with words, so you will have to think about them hard. Okay? So not everything I'm going to say will be completely obvious, but everything will be correct. And if you don't understand everything in real time, just remember the words and just know that they're true. And and that'll be useful, because as you think about it more, you learn more, you think more, you talk to more people, that knowing that thing is true will actually be helpful in your continuing understanding. So in the first part of the talk, I want to explain why space-time is doomed, what the arguments are that we have to get rid of this seemingly fundamental notion. And in the next part of the talk, I'm going to talk about one particular strategy for going about attacking this problem. There are many of them. But the one particular strategy that my friends and I have been pursuing for the past decade or so. And the first part is just, I'm sort of reporting from the front of what my friends and I in this subject have discovered over the last 30 or 40 years. Really, not me, I wasn't around 45 years ago, but anyway, the things that we've learned that we've collectively learned that set the stage. I like to describe where we've gotten to as the last 4 centuries have been like trekking through Nepal. You know, you land in Kathmandu, you get some Sherpas, you go, there are these complicated hills, you do all these things, and eventually, finally you get to base camp at Mount Everest, and there it is. There's the summit. It's sitting there, and you have no choice but to start going up. Okay, so the first part of the talk is to get you to base camp. Okay, just so you know what it is, what the problem is, why we have to do this crazy thing, And in the second part, I will tell you one particular approach. As I said, there are many others, and but I present it to you as an example, A, because it's what I'm actually thinking about, so it'll be more personal and fun, but also B, as an illustration of the way we go about trying to attack seemingly impossible to solve problems of the sort that I will explain to you in our business, and what the sort of methodology is to try to take very huge scale problems and break them into little chunks that you can do something about when you wake up in the morning. Okay, so that's just summarizing what I said quickly. We had two big revolutions in the first third of the 20th century in our understanding of physics. There are the revolutions of Einstein's picture of combining space and time into space-time, and in many ways, much more revolutionary developments of quantum mechanics. Now, these two pieces of physics are, in principle, even as they were discovered, are sort of separate intellectual frameworks. You could imagine a world that was completely classical, but which had a finite upper speed, and so that world would be relativistic. Or you could imagine a quantum mechanical world that didn't know anything about relativity. So there are sort of two different logical frameworks. And so the second those were established, theoretical physicists try to figure out how do you talk about universes that are compatible with both of these principles at the same time, that have quantum mechanics and relativity at the same time. And that turns out to be an incredibly difficult thing to do. A very, very constrained theoretical structure that's known as quantum field theory. Okay, so now, a particular quantum field theory, this famous standard model of particle physics, describes the particular elementary particles and interactions that we see in our universe. But quantum field theory more broadly is a sort of the general rubric in which we could imagine describing any candidate universe that's compatible with these two big principles. As I said, it's incredibly constraining. And incredibly successful. So these 12 decimal place accurate predictions that we make are very subtle calculations that agree with very subtle experiments. These are our principles. The pillars of our understanding are quantum mechanics and space-time. And that's what makes the storm clouds that we have now, the early part of the 21st century, so disturbing, because they're not some little detailed thing here or there that we don't understand, or some particular phenomenon that seems strange that we don't yet have an explanation for. That's par for the course. That's sort of normal science. All the time there's something you're confused about. Otherwise we'd have nothing to do, right? But mostly the things that you're confused about are explained within the basic framework that you have already. You don't have to turn everything upside down in order to deal with them. That's not where we are today. We can at least identify certain kinds of very simple thought experiments, and I'll walk you through some of them, that suggest something very big is wrong, that goes to the very foundations of what makes things so spectacularly successful. That's a paradox. On the one hand, those ideas of space-time and quantum mechanics underlie this, are the pinnacle of the 4 centuries that we've gotten to and work spectacularly well. On the other hand, I'm just about to tell you they've got to go. Okay? And so the challenge is to figure out how can they go, and why, if they have to go, were we faked into thinking they were there? Okay, and that's what I'll talk about in the second part of the talk. Okay, but what are the storm clouds? First, Space-Time is Doomed. That's the title of the lecture. And that's because of the presence of both quantum mechanics and gravity. So I'll explain why that's the case. There's even I didn't put this in the title of the talk because it would have been a little more technical, but in some sense, the second thing I'm saying is more radical. The first thing, all of my friends would agree. The second thing is a slightly more controversial statement, but I certainly believe it, that we're eventually going to come to see even limitations of the ideas of quantum mechanics. I'm not at all saying some crackpot thing like quantum mechanics is wrong or is modified in some crazy way, but that there are situations where quantum mechanics cries uncle. We don't know how to apply the rules to things that where the quantum rules have to be applied to making predictions about entire universes. All right, so let me just say a few things about these 2 points. First, why is space-time doomed? All right, so Here's a very simple thought experiment. By the way, I take it many people who give these talks have fancy animation and things like that. I'm a terrible artist, and there's no animation, okay? So all my pictures are like this. So if this bothers you, maybe we can stop and you can just leave right now, because it's just going to get worse, okay? So that up there is a magnifying glass, for example, okay? That is meant to be a magnifying glass. Anyway, but we're going to do a little thought. What I don't have in, is there a laser pointer up here? Or? Okay, fine. Yeah, what I lack in artistic beauty, hopefully, will make up in intellectual content. So here's what we're going to do. We're going to try to look at a region in space and time and just see what's going on there. I want to measure what's going on in some piece of space, and I want to see, can I actually see what's going on at arbitrarily short distances? Okay. Now, a basic fact about quantum mechanics that many of you know is Heisenberg's uncertainty principle. The uncertainty principle tells you that if you want to probe what's going on in shorter and shorter distances and times, you need higher and higher momenta or energies. Okay? That's why the big irony of the LHC, of the Large Hadron Collider, is it's a machine that's probing the tiniest distances we've ever probed. Thank you, sir. Thank you, thank you. Is the hugest machine we've ever built. Why is that? It's because to go to really tiny distances, we need really gigantic energies. And so we got to build these humongous rings where things are accelerated around and so on. All right, fine. So short distances means high energies. Very good. Now, in principle, there's no limitation to how short a distance you can resolve in that way. By the way, let me just, in order to explain, just to explain that again, if you're literally trying to look to see what's going on at very short distances, you need light whose wavelength is sort of comparable to the size of the thing that you're looking at. And then, because of quantum mechanics, you know that if you have light of a certain frequency, it just has to have a minimum amount of energy. It can't have a tinier energy than that. It has a minimum amount of energy given by Planck's constant multiplied by the frequency of the light. So that's why if you're trying to resolve what's going on at very short distances, you just must have incredibly high energies. Fine. In a world without gravity, there's in principle no limit to the tininess of the distance that you can probe in this way. You can just keep going forever. You just need higher and higher energies. You need to beg larger and larger multinational governments for more and more money, but in principle you can do it. But because of gravity, at some point something bad happens. What do you think happens? At some point, you're putting so much energy into such a tiny region of space. Now, roughly speaking, E equals mc squared. So like having a lot of energy in some region is like having a lot of mass there. Now, something bad happens when you put a lot of mass in a really tiny region of space. What happens? You eventually make a black hole. Okay, and there's so much mass there that even light can't escape from it. Okay? So that means that your effort to see what's going on in here eventually makes a black hole that makes it impossible for you to see what's going on in there. Right? Now, let's say after that happens, you get frustrated and you build an even bigger accelerator, even higher energies. What happens? Make an even bigger black hole. Okay? So this entire idea, in fact, this sort of basic reductionist paradigm that you go to high energies, go to short distance is eventually wrong. Okay, because of gravity. There is some distance scale at which it's simply impossible to probe what's going on at distances and times of that order. Now, if you put the numbers in, that's this famous Planck length. It's around 10 to the minus 33 centimeters. Okay? It's a minuscule scale. Remember, the size of an atom is like 10 to the minus 8 centimeters. Okay? The size of a nucleus, proton or a neutron, is 10 to the minus 14 centimeters. The distances that we're probing at the Large Hadron Collider are 10 to the minus 17 centimeters. It's 16 orders of magnitude away from that even. Okay? By the way, why is this distance so tiny? That's a reflection of how weak gravity is compared to all the other forces. Okay, gravity is ridiculously weak, but eventually, if you put enough mass in there, or enough energy, it becomes strong and it does these terrible things. So we can do this thought experiment that tells us it's simply impossible to give operational meaning to distances and times that are short compared to this famous scale, 10 to the minus 33 centimeters, 10 to the minus 43 seconds, which is how long it takes light to traverse that distance, and so on. Now, every time this has happened to us in physics before, that it's not even in principle possible to give operational meaning to some concept, it means that that concept doesn't really exist. It's something approximate, right? This happened to us with quantum mechanics, with the concepts of position and velocity of some particle. That's something that we can talk about in everyday life, we can easily talk about, but we know that quantum mechanics forbids you from knowing precisely what the position and velocity of a particle is at the same time. It's very important in physics to know and think about the things that you can observe in principle with perfect precision, because those should be the objects that your physical theory is about. And here we learn that space and time cannot be those objects, because we cannot actually do any experiments to resolve distances and times with arbitrary precision. All right, now, there's actually a more subtle aspect of this problem. Maybe I'll go over this part a little quickly, although it's quite deep and important. What I just told you might make you think that these difficulties are kind of localized to very short distances. Okay, but in fact, it's deeper than that. The difficulty is apparent on all scales. Okay, so here's another way of saying the problem, which does not involve very, very high energies. It involves experiments you and I could do in principle, but very accurate ones. Okay, and where again we run into, in principle, limitations on what we can observe. Now, this goes back to something having to do with quantum mechanics. Now, a very important fact about quantum mechanics, because the world is quantum mechanical, it's not deterministic. We can only predict probabilities. These are famous facts about we can only observe probabilities. A theory can only predict probabilities. So what that means is that if you want to get a precise answer in a quantum mechanical world, you have to do some experiment infinitely often, right? You want to verify that the odds of flipping a coin are 50-50. You have to repeat the experiment over and over and over and over again. And in principle, to get a perfect answer, you have to do it infinitely often. That's one infinity. You have to do the experiment infinitely often. There's another infinity that we don't talk about as much in undergraduate courses and so on, but is also important. Quantum mechanics forces you to divide the world into the finite system that you're looking at. But the thing that's looking at it has to be an infinitely large apparatus as well. Okay? And the reason is, if it isn't, then the apparatus itself has these sort of quantum jitters and jumps, and so there's an irreducible amount of noise associated with the finite size of the system, so of the apparatus. So let me just give you a concrete example. I am roughly made out of 10 to the 30 things, atoms, very roughly, okay? So let's say I want to measure anything, any quantity you want to name. You know, this famous magnetic moment of the electron that we've measured to 12 decimal places, let's say I want to measure it to better than that. I want to measure it to 10 to the 30 decimal places. So this is just pause how ridiculous this is, but I want to measure it to, let's say, 10 to the 40 decimal places. Well, I could want to do that. So here I graduate students, food, okay? I do the experiment, everything's fine. The 10 to the 10th decimal places, I'm flying, everything's fine. Death, no problem, right? No. But at some point, around the 10 to the 30th decimal place, something very bad happens, because I, as a finite thing, could actually, on that scale, spontaneously fluctuate into a cloud of dust. Okay? That would put a damper on making a precise measurement, figuring out what the 10 to the 30th decimal place is. One of the less bad things could happen. Maybe my brain could just have a little random quantum mechanical glitch, and even though I should have written down 7 in the 10 to the 30th decimal place, I wrote down 2 instead. Okay? You see, any finite system has in principle, error associated, because of quantum mechanics, with any measurement it can make. Now, that error is exponentially small in the number of things that you're made of. That's why it's of practically no significance at all, compared to the first thing that we talked about, where we have to do the experiment over and over again. That's a much more significant source of error. But conceptually, we need to do both things. We have to do the experiment over and over again, and we have to do it with an infinitely large measuring apparatus. And now we have a second problem having to do with gravity. The fancy word associated with it is that there's no local observables. But again, let me give the quasi-practical version of this. Let's say I'm trying to make any measurement of any quantity in this room, okay? And I'm trying to do it. I want to get the answer arbitrarily accurate. So I can't do it. I'm 10 to the 30 things. So I'll make some other apparatus. That other apparatus will get bigger and bigger and bigger, okay? I have to make it bigger and bigger and bigger, but the experiment is happening in this room, right? So if I'm going to fit all that stuff in this room, that apparatus, as I make it have more and more components, bigger and bigger, it gets heavier and heavier. And before I make it infinitely big, what happens? It collapses the whole room into a black hole. Okay, it's not one of these teeny tiny black holes, but now if you want to measure something with perfect precision, even on humongous scales, still, there's a problem. Okay? And by the way, it turns into a black hole, you have another problem that you can't do the experiment over and over again because you get sucked into the black hole singularity and die, okay? Inevitably. So that tells you that there is no measurements of any sort in the interior of a region of space and time that can belong as precise properties of the world. Those cannot be the things that laws of physics are about. Okay, so that's a very disturbing thing. Not only can't we do the sort of coarse measurement with the big accelerator that makes these black holes, but there's kind of no sort of measurement I can make in some finite regions in space and time that can possibly have any perfect precision associated with them. So these are the deepest reasons we are convinced that space-time has got to be an approximate idea. Now, what can we talk about? There are a few things left that we can talk about, and one of them is the following kind of experiment. What you can do is, we can't do the experiment in finite regions of space and time, so we do experiments that start and end at infinity. So what I can do is I can take some apparatus, make it bigger and bigger and bigger, but moving further and further apart from other apparatuses. I can use them to shoot some particles in to the interior of the space and time where they bang into each other. All sorts of stuff happens. They come back out, where they're measured in infinitely large apparatuses. Okay, so that's a perfectly reasonable kind of experiment that I can do, and where the results can be, in principle, perfectly accurate, right? So these kind of experiments are called scattering experiments for obvious reasons. The observable that you talk about is a scattering amplitude. The word amplitude there is because it's quantum mechanics. Something different happens every time when you collide two particles. Sometimes two things come out, sometimes three things come out. Everything comes out with some probability. The probability is the square of something called the probability amplitude, so that's the thing that we should be talking about. But the experiments don't happen in the interior of space-time. They start and end at infinity. Now, I've just given you very highfalutin reasons why these scattering amplitudes are interesting quantities, but there's a very practical reason they're of importance to particle physics, is those are the experiments we do. Okay, or very close approximations of those experiments are what we actually do. So, when we collide particles at the Large Hadron Collider, here's a picture of the ground outside Geneva in Switzerland. Of course, you don't see this oval on the ground, but the 100 meters under that oval, 27 kilometers around, there's protons going around one way, protons going around the other way, and they collide with each other. Now, of course, they're not literally coming in from infinity and going out to infinity, but 27 kilometers is plenty big compared to 10 to the minus 14 centimeters, which is the size of these little things. So this is an extremely good approximation to that kind of observable that we're talking about. Okay? So you send some things in, you close your eyes, some things come back out. Of course, in our mind's eye, we think what happened is, well, they went, and first this hit that, and then that happened, and something else happened, and then some other stuff came out. But all you really know is what went in and what came out. Okay? And those are the kinds of observables that we can talk about. All right, so that's the reason why space-time is doomed. Now, and the only kind of observables that we can talk about, the only kind of experiments that make sense, are not in the interior of space-time, but are somehow at infinity on the walls, very, very far away. Now, almost exactly 20 years ago, in fact, 20 years ago, 3 days ago, one of my colleagues at the Institute, Juan Maldacena, sort of revolutionized the field by making a big discovery in string theory of a sort of a set of toy universes where you could see these ideas in action in a much more concrete setting. Okay? Now, these are not our world, but they're the closest you can come up with to a universe that's kind of like the inside of a box. Physicists love to put things in boxes, okay? If you're not a physicist, you've suffered through our love of boxes in any physics course, okay? If you are a physicist, you love our love of boxes in any physics course. So physicists like to put things in boxes. It's hard to put a whole universe in a box, but this kind of universe that Juan played with is an example. So these are known as anti-de Sitter spaces. The words don't matter, but the sort of geometry looks like the inside of a tin can. But it has the peculiar feature that the spatial geometry inside is warped. And it's warped in the following peculiar way, that even though there's an infinite distance from any point on the inside to the walls of the box, it takes light a finite amount of time. If I shine a light here, it takes a finite amount of time for it to bounce off the walls and come back. Okay? So it's the closest we can come up to the notion of a universe in a box. Now, in this case, if you apply the same logic, you would say there are no observables on the inside of the box, right? So the only things that you can do is go to the walls of the box at infinite distance, and maybe you can ping the edges of the box, and waves would go in, and they'd crash into each other, and they'd come back out. So you do measurements now on the walls of the tin can, and those are the kind of observables that you should talk about. So this basic ideology would suggest that those are the kind of observables that you should talk about. But if that's the case, you might wonder, well, if the experiment sort of starts and ends on the walls of the box, what's the inside of the box good for, right? Well, one answer is, I can't figure out what happened unless I think there was a wave that went in and this hit that and then this thing came out. In other words, the inside of the tin can is a way of making sense of the results of the experiment, right? But could it be there's another way of making sense of the results of the experiments where I never say that the inside exists at all? I only talk about things out on the walls of the box. That's the amazing discovery that was made almost exactly 20 years ago, that in fact you can. And remarkably, you could completely forget about the inside of the box. You could imagine that there's a theory that just lives on the walls of the box, okay? The amazing thing is this theory doesn't even contain gravity. This is a theory that's very similar to the theory of the ordinary strong interactions in the real world, things that involve particles like quarks and gluons. But when the interactions are so strong between them that you sort of lose individual track of what the particles are doing, okay? And so only some collective excitations of the whole medium is easy to keep track of. In that limit, where the interactions become incredibly strong, what this theory, just on the walls, looks like, all the results of every experiment that you would do with such a theory are exactly as if there was an inside. Exactly as if there was an extra space there, that extra space had gravity in it, even strings, all the things that people in theoretical physics were excited about are actually completely equivalent to a totally ordinary theory of particle physics, albeit with very strong interactions on the walls of the box. So this is amazing. It's our first example. You see, I didn't stress it. I should have said it again. If space-time doesn't make sense, we know if space-time cannot be part of the fundamental description from the simple thought experiments I told you, we have to get rid of it, right? We have to find some new set of equations, some new set of ideas, principles that don't have the word space-time in them, but which somehow reproduce in some limit what we recognize as, nonetheless, recognize as a space-time. So the sort of buzzword is you have to come up with somehow space-time as an emergent thing out of ingredients that don't have it fundamentally. And this correspondence is our first example. It's a kind of baby example. It's a gateway drug to the idea of emergent space-time. It's a baby example because not everything emerges here. You see, very importantly, time does not emerge. There's a time that flows out on the walls of the box, and there's the time in the interior, and it's the same time. Okay, so space is emerging, gravity is emerging. Pretty spectacular already, but not time, okay? And so this is like a static, infinite universe, right? It's not our universe. We don't have this negative curvature. And in fact, our universe is expanding. Time is very important for our world. But it's our first example of what this idea of emergent space-time can look like. But if I go from our greatest success of the last 20 years to our greatest failure, it's that our universe, as I just said, doesn't look like the inside of a tin can. In fact, our universe is expanding. If we run the picture back in time, Famously, there's eventually, even provably, as Stephen Hawking and Roger Penrose taught us in the 1960s, inevitably back there somewhere, there's a singularity. There's a place where the equations break down. So that's what we colloquially call the Big Bang singularity, right? At the Big Bang, we don't know what came before the Big Bang because the notion of time is breaking down near the Big Bang. Okay, so there's something we really don't understand what's going on at very early times. Time is the important notion here that's breaking down. Also, at very late times, our astronomer friends discovered in the late 1990s that the universe is accelerating, not just expanding, but the expansion rate a few billion years ago started accelerating again. And that has a very startling consequence as well, because that means that what we see now in the universe is what we're ever going to see. We're never going to see more than we see now. There are things out there, but light from them will never make it to us because the universe is doubling in size at a uniform rate. And every little bit of time that light travels to us, the universe doubles in size and it doesn't make it to us. Okay? So what we see now is what we're ever going to see. We're not going to see any more. Okay? This is the best few tens of billion years in the history of the universe to do cosmology. Okay? But conceptually, this is a huge deal. Conceptually, it means there's a fundamental finiteness that's thrust on us by the fact that the universe is accelerating. Remember, I told you that in order to talk about anything with perfect precision in quantum mechanics, you have to have these infinitely big apparatuses with you. Well, you just can't do it. The accelerating universe means that you cannot divide the world up into a big infinite piece that does the looking and a little piece that's being looked at. Okay? So these are the hardest conceptual problems probably in fundamental physics today. I think most of us in the field think that these problems are a little too hard to do anything responsibly about right now. I mean, people mucked around with them for 5 or 10 years. They just seem really, really hard. Okay? And why is it hard? Because we not only have to figure out time is clearly the bugaboo here. So we have to figure out not just emergent space, but emergent space-time. And also, this is the first situation where it's conceivable that we need to extend our picture of quantum mechanics. And I say that not because, again, just to stress, I'm not saying quantum mechanics is wrong in any experiment that we might do in anyone's lab, but because the necessary condition for quantum mechanics to make precise predictions, namely infinite apparatus, finite system, simply cannot be realized. Quantum mechanics, the rules cry uncle, and we don't know what to replace them with. So both space-time and quantum mechanics, both together, are in danger. They're sort of are being threatened by this little observation that our astronomer friends made 20 years ago, that the expansion rate, instead of slowing down every 10 billion years, is speeding up every 10 billion years or so. All right. Now, so that's the first part of the talk. I hope to have convinced you. These are, as you see, these are very simple arguments. Okay, they're maybe a little subtle, maybe some of them are a little unfamiliar, but that's the nature we've learned over centuries. The nature of really good questions and really good paradoxes and things that are worth spending a lifetime thinking about in this subject are simple. You have to ask simple questions and not detailed, complicated things about some funny phenomenon. There are simple, basic things that go to the heart of the laws as we understand them. The questions are very simple to phrase and motivate, as I hope I've done. How to go about solving them is quite another matter. Okay, so that's what we're going to now transition to. But I think it's clear that what we're looking for are some new principles and some new laws from which the word unitary here means quantum mechanical, from which the usual picture of evolution in space and time have to somehow emerge together. Okay? So that's the more radical belief, and it's certainly my own belief, is that we're going to come to see not just that space-time is doomed and is replaced by something else, but that space-time and quantum mechanics are both things that have to emerge simultaneously from some more primitive substratum of ideas. And that's the sort of thing that we should expect to be seeing. All right, so now let's start talking about one angle into this problem. And again, I stress there are many, many angles. And if you got another one of my friends here, that would give you a totally different talk from this point on. but this is the story that I want to tell you about. So how do you go about working on this kind of a problem? Again, it's very good to know what the big questions are, but you wake up in the morning, you go to your office, you sit on your desk, and you can't just say, today I will work on Spacetime is Doomed. Okay, and now what, right? What do you have to actually do something, right? That even after tenure, okay, you actually have to do something. Death is a much bigger problem than absence of tenure, okay? So you don't want to waste your time on planet Earth, so you want to do something. So what are you going to do? This is such a large-scale problem. I think if and when we eventually figure it out, I think it'll be an even bigger transition in our thinking than the one that we experienced in going from classical physics to quantum mechanics, okay? After all, physics has been changed a lot over the last 400 years, but it's always been about describing how things change in space as they move through time. It's got to be a big deal to get rid of the notion of space-time. So let me give a kind of a parable. So imagine that we're previous to the transition from classical to a quantum. Imagine you're a classical physicist in, I don't know, the year 1840, and you're in bed, and you are visited in the middle of the night by the ghost of theoretical physicist's future, okay? And they say, I have a message for you from the 1930s. Determinism is gone, okay? The world is not deterministic. And they disappear into the night, as ghosts of theoretical physicists' future want to do, okay? So what do you do with this information? They've just told you that this thing that you thought was the bedrock of the Newtonian picture of the world, that the things are deterministic, that thing is wrong, right? You'd say, how the hell can that possibly be, right? Again, we'd be in a kind of very similar situation we're in now, right? You say, how can it possibly be? After all, it works spectacularly, clockwork universe, all this amazing stuff. How can it be that it's wrong? And if you wanted to do something to try to guess what was happening, it's clear you're not going to guess it, right? You're not going to, in one shot, go from F equals ma to the entire structure of quantum mechanics and Hilbert spaces and all the things that are there in quantum. You're not going to just do that in one shot. You could try to do some idiot things, like say, oh, I don't know, maybe there's some random terms I can add to Newton's laws. Haha, they're not deterministic anymore. It's cheap and stupid and also not the correct answer, okay? So what can you do? Well, I think there's one thing that you can do and say, look, if that determinism thing is not really there, then the determinism that I see in my laws right now, it cannot be so as necessary as I think to describing the physics. After all, the actual physics I have is compatible with this thing the ghost told me about. Determinism isn't there in the real thing, so there must be some way of talking about what I have right now under my feet in a way where determinism is not the star of the show, okay? And so, in other words, it motivates you to look around and say, if you know that some concept is going to disappear in the next level up, you should look and see whether there's some way of talking about what you have right now, under your feet, right now, in a way where that concept is not central, okay? It may not be obvious that it's possible, but if someone told you that it's going away, you're motivated to look for some other way of talking about normal things that you have now where that concept isn't central. So let me skip ahead here. So indeed, sometimes the most crucial clues are hiding in plain sight as funny features of the existing theoretical framework. And I had a couple of examples. But let me jump to the one which is the one I was just talking about. Newton tells you that the way a particle goes from one place to another is completely deterministic. You tell me what the position and velocity is now, and I go to the next place by F equals ma, okay? But you can ask, is there some way of talking about Newton's laws where somehow determinism isn't hardwired in from the start? There is, okay? And people, in fact, discovered it around this time, in the late 1700s and 1800s, people like Euler and Lagrange and de Maupertuis and others. And they were actually motivated by things that they had noticed about how light moves. So Fermat had noticed that light goes from A to B in a way that minimizes the time it takes to get there. Okay, so that's why light rays seem to move in straight lines in empty space from A to B. But if you have something where light moves more slowly in this medium than that one, then the reason it refracts is that it's choosing the way to make it from A to B with Snell's law that allows you to get there as quickly as possible. That's also why if you're on the beach and someone's drowning and you want to run and get there as quickly as possible, the way to run is precisely to satisfy something like Snell's law here as well, because you run more quickly on the sand than you can swim in the water. Okay, so by that analogy, people wondered whether there's some way of talking about how a particle moves from A to B, and they realized that there's a way of talking about Newtonian physics where you say that the way a particle goes from A to B is it sniffs out all the possible ways it could go from A to B, and it chooses the one for which the average value of the kinetic energy minus the potential energy is as small as possible. Okay, so that quantity is called the action, and so that's a totally different way of talking about classical physics. You notice in that way of talking about it, students when they first learn it, when that way of talking about it, it's kind of startling because it seems like it knows where it's going. Right? It doesn't look deterministic. Right? It looks like you're sort of sampling every way you could go and then making a choice about one way to go to get there. This, in fact, bothered the people who discovered it. They wondered why there was this totally, seemingly different philosophical way of talking about exactly the same equations in the end. Because when you figure out what those paths are, you discover they satisfy Newton's laws. So it's just a reformulation. It's just a different way of talking about the same laws. But somehow the laws of physics have this amazing feature. At any moment of our understanding, they can be formulated in seemingly philosophically radically different ways, from radically different starting points, even though the equations end up being identical in the end. And somehow it tends to be that one of them is the way they're discovered, but another one is the one that's necessary to make the jump to the next level of description. Because it's the second way of talking about things where determinism is kind of incidental. It's the second way that generalizes to quantum mechanics, you see. Not Newton's laws, but it's a second way. And in fact, famously, as Richard Feynman taught us, all that happens in quantum mechanics is really in a precise sense, you say the particle really does take all the paths from A to B, and there is a separate amplitude for each one of those paths, and you weight them in some way. And for big objects, you get the sort of biggest contribution you get is from the classical path. But the reason why, so first, this is now changing the story and is going from classical to quantum. But you see, there was a clue to the coming quantum revolution in the structure of classical physics. That's what's amazing. That is the answer to the question: how can it be that the rug is going to be so pulled out from under you when everything works so well? Okay. The reason that's possible is this some still miraculous feature of the laws of nature. We don't understand why the laws of nature have this amazing feature, but they do, that exactly the same laws seem to be formulatable from radically different starting points. And that's why, even though you think you've arrived at something that looks final and perfect from one angle, if you rotate it and you think of it as arising from another angle, you see, from this point of view, now it can be deformed and to go up to another perfect thing. Okay? All right, so that was the story with, that was a way, I just gave you a way that you could have imagined seeing or at least smelling the coming of the quantum revolution from the structure of classical physics. And there were these clues sitting there in the structure of classical physics, and that the Ghost of Theorist's Future could have even motivated you to discover these things. For all I know, the Ghost of Theorist's Future visited Euler and Lagrange, which is why they came up with this crazy way of thinking about things. They just didn't cite the Ghost of Theorist's Future. They didn't give them credit. All right. So that was all very philosophical and highfalutin for this part of the talk. But now I want to tell you at least one place where many of us think there's an analogous set of hints in the structure of completely ordinary physics under our feet for the looming disappearance of space-time and the simultaneous emergence of space-time and quantum mechanics from more primitive principles. Okay, and I'm going to go back to the LHC now. So we're going to, I hope you don't suffer too much whiplash. We're going to go from 30,000 feet down to very low to the ground, even 100 meters underground, and talk about very practical things, at least practical to high-energy physicists. Okay, so the LHC collides these protons. And this is the sort of typical thing that happens. The protons are made out of quarks. They're held together by particles called gluons. So a proton is not an elementary particle by itself. It's a big, messy bag. It's around 10 to the minus 14 centimeters big. And when you slam two of them together, most of the time they just smash apart. We don't care about that so much. But what we really are interested in are when the point-like constituents inside, these quarks and the gluons, they hit each other head-on, something new happens. Okay? And just so you have an idea of the kind of rates here, there are sort of 1 billion collisions every second at the LHC. And the kind of rate at which you make particles that you care about, some of these things you haven't heard of, or maybe you have, top quarks, these are things that exist. Experimentalists are still looking for things that are called super partners of ordinary particles. If they're there, if we're lucky and they're there, we haven't seen them yet, but if they're there, we're maybe making one of them every minute, even though there's billions of collisions a second. Okay? So that gives you an idea that ordinary stuff from the ordinary quarks and gluons banging into each other is happening billions and billions and billions of times higher rate than the needle in the haystack that you're looking for. Okay, so obviously, in order to be able to extract useful information from the LHC, you have to learn what the rate is for these totally ordinary processes. Okay, so you can have two quarks hit each other and two quarks come out. Well, they actually turn into jets of strongly interacting particles. They don't come out as quarks. But anyway, two things go in, roughly two things go out, or three things come out, or four things come out. And you have to learn how to calculate those things reliably enough to be able to subtract them and look for something new. Okay? And that's why national labs and places like CERN hire theoretical physicists to do these difficult calculations. Okay? In principle, this is like an engineering problem, quote unquote. Okay? We know the laws, everything is fine, someone just has to sit down and do these calculations. So what do the calculations look like? Well, Richard Feynman taught us how to do these calculations. Okay, and many of you have probably seen these famous pictures that the way you figure out how particles bang into each other is to draw Feynman's diagrams. These are legendary things. Feynman even painted them on his van, right? Now, when you teach courses, you tend to give problems where like two particles come in and two particles go out. Okay, and half of your graduate students don't know how to do they flunk that problem set, so you don't take them. Okay, half of them can do it, so they're candidates for maybe being your students, right? But that's not good enough for the LHC. You need to be able to do calculations where like two gluons come in, these are the particles in the proton, two gluons, maybe three go out, or four go out. In fact, you have to do up to like 8 or 9 go out, even. So what is it that actually happens? You have to just draw all these pictures. Okay, it starts looking a little bit complicated. This is what the actual calculation looks like. Okay, 100 pages of things that look like that. 100 pretty dense pages, right? That's if you have like 2 particles in and 4 go out, right? Okay, fine. Nobody promised you, not every question in physics has to have a simple answer. In fact, part of the chauvinism of this part of the subject is we declare as most interesting those questions that have simple answers. And the ones that are complicated say, well, they're just complicated. Someone's got to do it. The computer does it. Somebody does it. Okay, it's not deep. Okay, but these poor guys, whether it's deep or not, they actually had to do the calculation. The experimentalists needed the answer. Sorry, one way or another, you got to do the calculation. 100 pages is still too complicated. Physics is a wonderful way of rewarding morally good behavior. Okay? And what these people, almost 30 years ago, actually, the first example, what I'm about to just tell you, was done almost exactly 30 years ago. They discovered that when you finished, they pulled out every trick in the book, and they already had a breakthrough paper when they got from 100 pages to 10 pages, and everyone was super excited. And then after a little bit more work, they found that everything collapsed to a single term. Okay? Now, I'm not explaining what these little funny symbols mean, but they're a measure of the energies of the particles involved. Okay? Those hundreds of pages involve massive amount of cancellations, so the final answer is one term, just that. Right? Isn't that amazing? Now, this makes something clear, and back then it was not universally appreciated. You know, and it's okay that it wasn't universally appreciated. It was not appreciated as the tip of a giant iceberg. Today we know it's a tip of a very giant iceberg. But this already shows you that Feynman's way of doing this physics, it does something. What it does better than any other way of doing the calculations is it makes the rules of quantum mechanics manifest and the rules of space-time manifest. After all, those are both the things that we talked about. You draw a picture in space and time, okay? And you have to add up every possible path that was taken in order to make it quantum mechanical. You do those two things, and that's what you get. You get these pictures, thousands of pictures, hundreds of thousands of terms, hundreds of pages of algebra. If you want to make space-time and quantum mechanics manifest, you're led to believe that the answer is very complicated. And yet the answer is shockingly simple. Okay? So it's clear that making space-time and quantum mechanics manifest is hiding something else. And we should therefore try to figure out what that something else is. Okay, we should try to figure out what the principles and laws and rules are that brings this simplicity to the fore. And by doing that, clearly that way of doing things will not have space-time and quantum mechanics as the stars of the show. It'll have some other ideas as the stars of the show, which we don't know what they are yet, but we can start trying to discover what they are. And hopefully, if we understand them well enough, we can then see how, from this second starting point, the description where it does have space-time and quantum mechanics comes out. But you see now, immediately, there's something much more concrete that we can get to work doing, right? First, we can learn how to try to do these calculations. You know, they did this 30 years ago. When you tried to do already the next most complicated case, again, it looked horrendously complicated. Okay, so their methods were no good for the next most complicated case. That was one reason people did not immediately see that there was something going on. They just thought it was kind of an accident because they didn't see simplicity everywhere. But the first thing to do is say, well, you dig a little more and see, can you actually calculate these things, see what the answer looks like? This is to get data. It's like theoretical data. You want to see what the actual answer looks like. And then next, after you see the answer, can you think of some structure that gives you the final answer from some different starting point? Okay? So that's the sort of strategy that we can pursue. And in just my last few minutes, I'm just going to really fly through some of the ideas, just so you have an idea, just even a rough sense of the kinds of new ideas and structures that show up. Because it gives you a sense, you'll get a sense for, on the one hand, how simple and basic they are. On the other hand, they're much more abstract and alien to standard physical pictures than we are used to. I'll skip over that. So I can say that this subject has been developing really for around 30 years. It's accelerated a lot over the last 10 years or so. And one of the lovely things about it is that it combines a lot of ideas from different parts of theoretical physics, a lot of input from string theory, this world in a box picture. Roger Penrose's darling from the 1960s, that was the ugly duckling of theoretical physics for a long time, twistor theory. It has an absolute role to play in this story. There are things that people doing atomic physics and thinking about things like spin chains, they've run into structures that are very relevant. And very excitingly, new structures in mathematics. And things that are even new to mathematicians or that they've been developing just over the past decade for completely independent reasons. We've been finding that this physics, the physics of trying to think about particle scattering without space and time, is intimately related to very new parts of mathematics in a way that is being really fruitfully explored by both physicists and mathematicians together now. But all these things are converging on some new formulation of completely standard physics where space-time and quantum mechanics are not inputs, but are our outputs. All right, so let me give you just a flavor of the kinds of physical ideas that are involved and the kind of mathematical ideas that are involved in this emerging picture. Because, as we said, on general grounds, we should expect that there's some new physical ideas and that there are some new there have to be some new mathematical ideas associated with them as well. So the physical idea begins with a very simple observation. You don't need to know what any of these symbols mean precisely, but that if you look at the very simplest possible interactions, very simplest possible scattering processes, where three particles come together at a point in space and time, the answer for those things are not complicated. They're incredibly simple, and they're furthermore, when you understand things a little bit better, you don't even actually calculate anything. They're entirely determined by basic symmetries of the problem. Okay, so there isn't even really a calculation to do here. These are sort of totally nailed, kind of God-given, simple objects. So those things are incredibly simple. So why do we get these hundreds of pages? The reason we get these hundreds of pages is because what Feynman tells us to do, you see, the particles that we're talking about there are real particles. They move from the infinite past to the infinite future. They start in some experimentalist detector. They end in some experimentalist detector. They're real particles. Whereas in all these pictures of Feynman's diagrams, all these things on the inside, none of them are real particles. In fact, even in the lingo of the subject, we use the word virtual particle to talk about them. Okay? They're not actually real things. Nobody sees them. They're all in our head as a story we're telling on the inside in order to explain the outcome of the experiment. And you can clearly, technically trace all of the horrible complexity of the final answer to these virtual particles. So the physical idea is to just never talk about virtual particles. Just eliminate virtual particles. Okay, if you're going to eliminate virtual particles, what can you do? All you can do is take those basic interactions where all the particles were real, and you can glue them together in a way where still all the particles are always real. So these are not Feynman's diagrams. They're very different kinds of diagrams. I didn't explain why you had these black and white vertices, but there are two different, the particles we're talking about here are the quarks and the gluons, and they have a spin. They can spin either in the direction of motion or opposite to the direction of motion. That's these minus, minus, plus, or that should have been plus, plus, minus. So these are things that are spinning in their direction of motion. That's something spinning opposite to its direction of motion. So there are two different possible configurations you can have, and that's what the black and white vertices are about. So you can glue the black and white vertices together where everything inside is real. Everything is a real particle. And so you can just ask what you get. So these are not Feynman's diagrams, but they're the only thing you can do if you refuse to say the word virtual particle. And if you start playing this game, just gluing these Tinker Toys together and seeing what kind of answers you get, you discover something amazing. For example, you discover that if you glue sort of these things together for 2 particles in and 3 particles out, that this single diagram is the result of the sum of 30 pages of algebra with Feynman diagrams. Okay? So get rid of virtual particles, immediate benefit, right? You actually directly write down the answer as this absolutely directly physical process. That's pretty cool. Now you go to the next most complicated case, and you discover that this picture, just gluing a little bit more on here, and then you have to add 2 more that look exactly like this, just with these indices rotated around a little bit, that the sum of those 3 terms reproduce 100 pages of Feynman diagrams, all right? So this is good. Thinking about these physical-only processes is good. But there's a fascinating rub. The rub is that while each one of these diagrams of Feynman's are sort of designed to make it look like there's quantum mechanics and space-time there, that's the point, right? Things moving in space-time and splitting and so on. You can show that starting with this example, that one's a little special, but starting in this example, each one of these pieces cannot be given an interpretation in terms of a process that takes place in space-time, and that is compatible with quantum mechanics. So, and you learn more things. You learn that there's actually a large number of ways. You see, there's one set of diagrams you draw here over and over again. But for the same process, you discover there's a huge number of different ways of expressing the answer when in this kind of language. So, and if you write down the expressions, that they don't seem like they'll add up to the same thing, but they're miraculous mathematical identities that are satisfied between them that guarantees that the final answer ends up being the same. So it's clear that these physical-only processes somehow, on the one hand, they give us the right answer. On the other hand, they're controlled by another world of ideas somehow. They're coming from somewhere else. They don't care about space-time. They don't care about quantum mechanics. They care about something else, And they're the origin of all the simplicity in the final structure that we see. So all of these things started pointing to a picture that we should think of this final answer. We should think about the amplitude, roughly speaking, as the volume of some region in some space. This was like a fantasy around 5 or 10 years ago, that if I give you the energies and directions that all the particles are coming in, with that information I build some shape in some auxiliary space, and the volume of this shape would give me the answer. The volume would give me the amplitude for the process. And if I actually wanted to calculate the volume, I'd have to break it up into a bunch of little pieces in this way, and each one of those individual ways of expressing the answer, as I just showed you, would correspond to one particular way of breaking it up into a pieces. So that was a kind of a picture for what was going on. And in fact, that's something that eventually, at least in a theory that in leading order of approximation is literally exactly the same as the theory of the strong interactions in the real world, but at the higher orders of approximation differs from it and is the more symmetric cousin of that theory. That picture has indeed emerged in the last 4 years or so, where if you give me the data of the energies and the momenta of all the particles, the energy and the momentum is sort of 4 variables. So each particle, there's 4 variables associated with it. So if there's 10 particles, you give me 10 4-dimensional vectors. With that external data, you build a shape in this auxiliary space, and indeed, the volume of this shape literally calculates the amplitude. So that's the end result. That's the physical motivation, was to get rid of virtual particles, and we see that there's this very abstract underlying object that seems to calculate these amplitudes. Now, let me just give you quickly a flavor of the mathematical ideas that went into building this object. And we start from a very simple starting point. If you imagine that you were telling a mathematician that you're scattering a bunch of particles, they would say, I don't know anything about physics. So what matters for your particles? You say, are there energies or their momenta? They say, I don't know what energy and momentum is. Their spin, I don't know what those things are. So what's left? Just their labels, okay? Oh, okay, I can do something with labels, okay? So how do you scatter things if you only have labels? You just permute them, okay? So that's it. So this is the most basic scattering we can imagine. 1, 2, 3, 4, 5 just gets permuted to 3, 5, 2, 1, 4. Right? Now, that just seems like an absolutely idiot thing, okay? But in fact, for around 30 years, it's been known that this picture of a permutation is actually beautifully associated with the picture of scattering. As you'll see, not for things related to the real world, but we'll come to the real world in a second. So this is how you can make it look like scattering. Just draw the permutation. You see, here's 1, 2, 3, 4, 5. And I draw them again up here, but I just draw 1 goes to 4, 3 goes to 1, 2 goes to 3, and so on, okay? Now, all of a sudden, this starts looking like a picture of particles moving and scattering with each other, right? If you think of that as time and this is space, then it really looks like, oh gosh, 1 is moving, 2 is moving, 3 hits 2, they all hit and scatter against each other, okay? And in fact, there's an old story, really goes back even more than 30 years, that really precisely relates permutations to very special systems in one dimension of space with particles moving and scattering against each other, okay? All right, now, people have been impressed with this. It's a very beautiful picture. People have been impressed with it, but it always seemed like it's a very special thing to only having one dimension of space, okay? And in particular, it can't apply to the real world. There's no creation and destruction of particles. All that happens here, the fundamental interaction is just 2 things coming in and 2 things going out, not the ability for one thing to decay into 2 things or 2 things to create 1, which is what we have in the real world. However, in the last decade or so, a little bit more, people have learned how to associate, people have learned a new way of representing permutations in a graphical way. And it goes like this. So let's say I want to represent the permutation 1 goes to 3, 2 goes to 1, 3 goes to 2. What I do is I don't put 1, 2, 3 at the bottom and 1.2, 1, 2, 3 at the top. I just put 1, 2, and 3 on the outside of a circle, and I draw a little black vertex on the inside. And the rule is that in order to see where does 3 go, I walk into the graph, and if I hit a black vertex, I make a right turn. Okay? Now, with the white vertex, when I hit it, make a left turn. That's it. Now, glue them together any which way you like. And the claim is that every permutation can actually be realized by some way of gluing black and white vertices like this together. Okay, so that gives you this funny permutation. 1 goes to 3, you go in, you turn right, left, right. Okay, so just these dumb pictures with black and white vertices are now ways of representing permutations. Now, of course, we've just seen moments before in physics these pictures with black and white vertices. And believe it or not, these are identical pictures. Okay, so every permutation can be represented like this. And then, this begins to become more technical, but we start with an object which is fundamentally determined by this idea of representing permutations graphically, but then associated with it canonically are, and in a very, very simple way, are some geometric notions. The geometric notions, in turn, are generalizing very simple things like the notion of the inside of a triangle or the inside of a tetrahedron. We can have simple notions like this that are slightly generalized into larger mathematical spaces. And so every one of these pictures first starts off life as something that represents a permutation, but quickly becomes associated also with an interesting set of mathematical objects, matrices, for example, that have the funny property that all the determinants, all the 2x2 determinants in these matrices are positive. Or I can get a general matrix with some number of rows and some number of columns. The only game that you want to play is that all the determinants of these matrices are positive. That game turns out to be completely related to these pictures with black and white vertices, completely related to this way of realizing permutations, and completely related to the physics in the end. Okay? So there's just one basic object, this interesting way of representing a permutation that gets lifted through a variety of structures until it ends with a scattering amplitude at the top. Okay? So again, that you're not meant to understand any of that, but just so you got a flavor. I just wanted to get you a flavor of what are the ideas that are involved here. If we're going to replace space and time with something else, we can't have space and time. So what could we have? We have to have much more primitive things around. We have to start with much more primitive and basic mathematical ideas, and that's indeed the kind of thing that we have been. That's indeed the kind of thing that we've been seeing. Just to give you a concrete example, I told you that there's this concrete geometric object, this thing we call the amplitahedron, and that the volume of that space calculates scattering amplitudes. Well, let me give you an example. So if you want to calculate just 2 particles in, 2 particles out, but what in Feynman's language would involve more and more complicated pictures on the inside with more and more internal loops of particles. These are the calculations. At the LHC, we need to do them at 1 loop and maybe 2 loops. But they get really incredibly, incredibly complicated. You would never dream of forcing a graduate student to even do a 1-loop calculation. Okay, but so these are quickly the number of Feynman diagrams is larger than the number of atoms in the universe. Okay, those calculations are replaced by a geometry problem of the following variety. Just you see, it's a problem I can describe to a kid in grade 8. You have a 2-dimensional plane. You imagine you have some red vectors and some green vectors, and they're all in the upper quadrant. So that's the first requirement. They're all in the upper quadrant. And they just need to have the following property, that if you take the vector from any pair of A's, like A1 to A3, it should always point in the opposite direction as the vector between a pair of the B's, the same pair of the B's. That's it. So just solve that geometry problem. All the possible configurations of red and green vectors in this upper quadrant that satisfy this property. If you solve that problem, there's a dictionary that converts the solution to that problem to the answer to this calculation with space, time, and quantum mechanics in it, okay? All right, so in this example, we begin to see the kinds of ideas that could show up. Indeed, the final answer is the volume of some region. You can break up the region into lots of little elementary pieces. Each one of the pieces are one of these simple pictures. There are many different ways of doing it, but the final answer is always the same. Crucially, the pieces don't have a space-time or a quantum mechanical interpretation, but the full volume does. And in a very precise way, the rules of quantum mechanics and space-time emerge as sort of derivative notions from this underlying geometry. And I'll just end with this picture. This is a process that you could care about at the Large Hadron Collider. You might imagine 2 gluons coming in and 6 gluons going out. That's something that actually matters. And so if you wanted to calculate, again, not hundreds, thousands, I don't even know how to count how many pages of Feynman diagrams it would be. But if you want the leading, the leading contribution to the rate for this process, in this picture, you would literally draw a shape like that. Okay? So you would take the energies and the momenta of the particle. The energies and the momenta of the particle would tell you to draw, not in space-time, in some funny abstract space. In this funny abstract space, you draw a picture, and then you just compute the volume of that thing, and you're done. Okay? So there's a long way to go to make these things fully realistic, but we're at a starting point where in leading approximation, these ideas that we're talking about actually describe the real world. And they also show us, in a very concrete way, how it might be that the rules of space-time and quantum mechanics emerge together, sort of hand in hand, from more primitive building blocks. All right, so I hope that at least from the first part of the talk, you got an understanding for why we're at a sort of dramatic moment, and we need big new ideas. It's not clear yet exactly the shape the big new ideas will take. There's lots of different kinds of work going on in many different directions in the field. I gave you a snapshot of one of them in the second part of the talk, but I hope from that part you got at least a sense for how we go about attacking these problems. You can't attack them in a completely direct frontal way often. You have to go a little bit sideways, find some slight cousin, some question that has some of the flavor of the big question that you're trying to solve, but which has enough chinks in its armor that you can start making progress on it. And so what's nice about the particular subject I told you about, apart from the fact that it's actually directly relevant for experiments, or related to things that are directly relevant for experiments, is that there's a notion of right and wrong. You know, we can decide if we've managed to compute something that we couldn't compute before. We can check whether it's right or wrong. We can check, since we're not putting in the rules of relativity and quantum mechanics, space-time and quantum mechanics, we can check if they nonetheless agree with them when we're done. All right. I think this has been, even this little part of it has been an exhilarating adventure so far. One of the things that I find very interesting is that physicists and mathematicians have been working together in this subject. A lot of the developments relating physics and math have a storied history going back centuries, but normally one subject or another is ahead, knows more about what's going on, and then tells the other one what to do. And this is a little bit unusually, of course, it's also very recent, so we'll see how it develops, one where we're both seeing exactly the same kind of ideas from radically different starting points at roughly exactly the same time. And so it's in a fruitful and meaningful way we're actually talking to each other. But it's also clear that we don't have a grand synthesis. If we had one, I could give you a normal length talk about it. So the grand synthesis is yet to come, so hopefully someone will find it in 10 or 20 or 50 or 100 years. And I trust the Cosmos Club will still be around on that time scale. So someone will come tell you about it. Thanks a lot.
So we have time for a few questions. There is a procedure for the questions. We have 3 people with microphones who will be running around the room to bring the microphones to you. We have a new colorful addition to our microphone procedure. We have a bright red microphone and a bright green microphone and a bright blue microphone. And so I will be able to identify you. And when you get the microphone and you're identified as blue, green, or red, please stand up. Please tell us your name. Please tell us if you're a member. There's no penalty for not being a member. And then ask a question. So we'll start with Joel with the green microphone.
Oh, thanks. Dr. Nima, thanks for your presentation.
And you have to hold the microphone very close to your mouth.
Okay, thank you for your presentation, sir. Joel Wilson, member. 2 questions. With the amplitude hedron, I guess I kind of cheated a little bit. I tried to read some of your papers on it. You talked something about a positive geometry in which it's embedded.
Right.
Is your sense that that's kind of, I don't know, it's might not be a good question, the real thing out of which it's the primitive, the geometry is the primitive?
Well, I think it's fair to say it's such early days in the story. It's a very bad idea to take the latest thing that you understand and think that's the real thing. But I think what we can with confidence say is what's not the real thing. Okay, and so that's the kind of the whole point here is to sever as much as possible, to eviscerate as much as possible all of the usual language and comfort and luxuries of having a picture of a space-time and having, if you're doing quantum mechanics, if you're a physicist, you have a Hilbert space. You have all these spaces that you're used to. And if you see any of them around what you're doing, from this point of view, you're doing it wrong, right? We have to get really uncomfortable, right? We have to go somewhere. We just have to cut the cord. We have to be in territory that just does not feel like that. We're clearly in territory like that, okay? So now, at every point, we have a provisional understanding for what we think the most important thing is, and it changes every 2 or 3 years because it's still developing. So right now, yes, it seems like, certainly in the kind of stories that I'm telling you, what replaces the rules of space-time and quantum mechanics are things that loosely are just the existence of some geometric shapes. And it's what just to give a slightly concrete idea of what it is you check. Like if I hand you some answer, if I hand you the rate to see what happens when 2 things go in and 2 things go out, how would you check that the answer is compatible with the principles of space-time and quantum mechanics? Well, one thing that you know is that when do any kind of amplitudes in physics become large? It's when you have some kind of resonance, right? So if you're sitting on a swing, if you sit on resonance, the amplitude becomes larger and larger and larger. So that means in this context, if some particles come in and they have the ability to make a real particle that then travels a long distance and then spits back out to a bunch of other ones, then you'll have a big amplitude for that, just like the resonance on the swing. So that's one way of checking. If someone hands you a formula that says and claims this is the amplitude, you have to see, well, where does it blow up? Is there any place where it blows up? And it can only blow up in that kind of configuration where a bunch of the particles have the ability to make something that then goes out and decays, and then it has to blow up in a very specific way to be able to interpret it that way. So those are the things that Feynman's diagrams make blindingly obvious. Mm-hmm. So now you can ask, if you don't have the picture of space-time, if you don't have the picture of quantum mechanics, where is that going to come from? And the answer is that comes from the geometry. Mm-hmm. So there is a dictionary. The dictionary says that where the amplitudes blow up corresponds to moving to the faces of this geometry. Mm-hmm. And then the fact that the way it blows up is in splitting in 2 is reflected in the fact that when you go to the face, you actually see on the face the geometry sort of splits into 2 lower pictures of the geometry. But all those things are not being put in by the existence of an underlying space-time picture, but they have their own purpose in life that comes from these geometric starting points. So if I stop there, indeed, the positive geometry, as you say, would be the star of the show. Mm-hmm. But we're so far from being done that I imagine that it's going to go through many iterations before we figure out what the actual principles are.
Thank you, sir.
We have a red microphone back there somewhere.
Hi, Tom Hartman. I forgot to sign up for membership the last time when I went home the last time. So I'm going to make sure to do it this time because I do enjoy these lectures. I've been here a few times. One thing, if I'm understanding the problem correctly, it's what you're basically saying is you're looking for the first principles that emerge into what we have been calling space-time and quantum mechanical theory, and that's what we don't have. So how did you draw the diagrams if you don't have those principles?
We don't.
So like where do the rules come from for drawing those diagrams? That's like how did you come up with
Yeah.
that?
Well, that's why it's an adventurous subject. So we don't have the rules. We have to come up with the rules. So it's not, but it's not quite as bad as it seems because we know something about the final answer. So that's a big key thing, right? We have a lot of data, theoretical data. We have data what the final answer, because remember, we're not changing anything here. This is really the analog of looking for the principle of least action. We're not removing space-time and quantum mechanics. We're just trying to find a way of talking about them, talking about this ordinary physics where it's not there, with the hope of finding the right grammar, the right words, or the right language that will get us in the right mental space to be able to make the bigger transition where we actually remove it. That's what's ultimately needed. But because of that, we have a great luxury that we know the right answer in many cases. We have a lot of data. And so that's a big guide to what you should do. And in particular, when I drew those pictures with black and white diagrams, the reason it was completely nailed what kind of picture I could draw is that the simplest case, where just three things come together, in that case, quite beautifully, you didn't need Feynman to tell you what the answer was for that most primitive simple case because the answer could only be one thing, just dictated by very simple, essentially just symmetries of the problem. So there are some things that are just locked. You don't need any rules. They're just sort of essentially dictated by the symmetries of relativity. But now you can ask what you do with them. And now you have to decide to play a game. What happens if I glue them together, right? I ignore the fact that it doesn't look like Feynman diagrams. I mean, they could have done it at any point in the last 60 years, played that game. But when you're motivated to do it like this and relax for a little while and just see what happens, then you start making these interesting observations. My goodness, if I put them together in this way, just this one picture gives me the whole answer. And then it starts developing from there.
The green microphone back there, and if anybody has a question, please keep your hand up long enough for the microphone runners to see you. So we have one on the way back there. But the green microphone, yes.
Yes.
My turn?
Yes, green
Okay.
microphone.
Wonderful. Could you hear me?
Yes.
Okay, wonderful. Thank you. I am Elena Keith with Your Citizen Project, and I'm a guest of Vice President of the club, and happy to be here. And Nima, thank you so much for this is terrific, and I definitely would like to acknowledge you. You step outside what's comfortable, so you are in definitely uncomfortable space, and that's the space where we create and we find new things, so the space of discovery. So this is terrific. And the question that I have, did you get to see parallels, so to say, correlation with what we call 1.6 golden mean? It looks like positive geometry, what we call positive geometry is based on the number consistently whenever the matter wants to be organized. And when we go into disorganized space, chaos, or whatever's negative geometry is, it's not based on the number.
Oh, in that sense, you mean? You mean like hyperbolic versus positive? Yeah, it's
Right.
not, there's no direct relationship. There's no direct relationship yet. I should say that there is some important, that it is interesting that this inside of the tin can universe that so much progress has been made with is negatively curved. But there is a sense in which these shapes are convex, so they are positively curved. So there is a difference, but they're in totally different spaces. So I don't see any direct relationship, unfortunately, yet.
We have a red microphone question.
My name's
Yes.
Rudy Krutar, and I am once and future member of the club. I have a
society.
fundamental question that your notion may answer. Is the Planck length, does the Planck length diminish with the Lorentz-Fitzgerald contraction?
No, it does not. No, it's not. I mean, it's not a, no. In no meaningful sense does it, it's not, there isn't like a little rod sitting there. In fact, this is a very important point. So we're being a little loose when we talk about the Planck energy, right? Because, of course, an actual energy would depend on the observer and so on and so forth. What we're really, but there is something which is observer independent, which is not just the energy of one particle, but if you have one particle here and another particle there, right? Then the kind of, the violence of that collision is something that all observers agree on, okay? So while, for example, we say that at the Large Hadron Collider we're colliding protons at, roughly an energy 10,000 times bigger than the MC squared of the protons. What that means, if I go to a frame of reference that's moving incredibly quickly in one direction, then I could make the energy of one of the beams vastly bigger, okay? But then the energy of the other beam would be vastly smaller. And there's something that everyone would agree on, is that the LHC produced a Higgs particle. Okay? It had enough energy to produce a Higgs particle. There's something completely invariant, which is there not for the energy of one particle, but something involving two of them colliding. So when we talk about the Planck energy, we're talking about those kind of physical experiments. When I'm trying to probe very short distances, that's what I'm doing. I'm sort of colliding particles at higher and higher energies, and that's what will eventually produce a black hole and cause all those problems. And that will happen at the same value of that energy and the same value of that inferred length scale for all observers. Okay, however, what you say raises is the answer to a very, very important point. You see, you might have thought that all this business about space-time breaking down just is pretty boring. After all, the notion smooth surface of table breaks down. Looks like a smooth surface, but I know when I go to very small scales, it's made out of atoms and molecules and stuff like that, right? So why isn't it just atoms of space-time? Oh, it's no big deal. Like, why are we making such a big fuss, right? We've seen all the time things that look smooth turn into things that look choppy when we see they're made out of microscopic constituents. So why isn't it just that? It's just atoms of space-time. It can't be that, and it can't be that because of your point. Because for it to be atoms of space-time, it's very important that those atoms are small. But small in whose frame? There is no universal notion of small in whose frame, you see. And another way of saying it is that we can say that the table is made out of stuff because the table chooses a frame. Okay? But we can't say it about the vacuum without breaking Einstein symmetries. So that's why you can't just have atoms of space-time. The notion of atoms of space-time is in radical conflict with Einstein's relativity. If it wasn't, this is another aspect of the problem I kept mentioning, that relativity and quantum mechanics, space-time and quantum mechanics, these two things that put such a ridiculously tight straitjacket on our imagination. If we just had one or the other, life would be much easier, much less constrained, and many fewer people would be working on it, because there'd be no point. Okay? After all, you could have made a justifiable, you can make a justifiable complaint. All this stuff at the Planck length is happening at energies 16 orders of magnitude bigger than anything you can do with your accelerators. So aren't you just making crap up, right? It's a great work if you can get it, I guess, right? You just sit there. I think this is going on. No, I think that's going on. I think this is pretty. I think that's lights. I like strings, violins, cellos, Nova specials, right? If that's what was going on, that would be a complete intellectual disaster, right? And the field would be just bullshit. That's not what's going on. And it's not what's going on precisely because it's almost impossible to monkey with the rules without breaking something. And so despite the fact that we can't actually do experiments at the Planck length or Planck energies, even if we imagine trying to write down something which grapples with these problems, which is not automatically dead, not by new experiments up there, but by all the old experiments that told us that relativity and quantum mechanics are right, that is such an incredibly high bar to pass that essentially only one theory has even come close to passing it over the last 50 years, and that's string theory. That's why people work on string theory. It's not there's clubs and cliques and these people like it, they think this is pretty, that's pretty. There's an actual beefy accomplishment to write down some concrete formulas that don't violate relativity and quantum mechanics and fix something up at very high energies involving gravity. Right? No one else has done that. Doesn't mean that it's right, but that's why we have, because there might be, if we work another 50 years, someone will find a second way that's radically different than that one. Then we'll be in an interesting situation. You know, we'll have two, and we'll need an experiment up there to tell us which one of them is right. But that's why the maturity of the subject matters, because you don't need new experiments to rule out ideas. 99.999% of your ideas are wrong already, out of the box, because they violate all the old experiments that gave us these big principles to begin with. So, but anyway, your question about the Lorentz contraction of Planck length is one of them, because that's a word-level idea. Oh, just make some crystal, atoms of space-time. That's just dead, out of the box, okay? So you have to do something more subtle. And all the things I'm telling you about are much more subtle than that. You know, this world in a tin can picture, this holographic picture, that's way more interesting, right? It's not like you just put the inside on some kind of crystal or lattice. No, it's this other theory that lives on the walls of the box and all this fancy stuff. What I was just telling you about in the last part of the talk, again, even more alien, more abstract, all in an attempt to grapple with this question of where space-time comes from, precisely because we can't mess with relativity.
3 more questions. It's going to be green, and then it's going to be blue, and then it's going to be red.
Oh, we don't have white? What are we doing?
Disappoint you all.
Vladimir Dergachev, I'm not a member.
And then we'll take one from our live stream.
First of all,
the question?
thank you very much for the talk. And,
Oh, there you are. Okay, good, yes.
Beautiful mathematical
What's your
ideas
name?
in there.
What's your name?
Name? Vladimir Dergachev. I am not a member.
Okay.
So thank you for the talk and the beautiful mathematical ideas. And I have a question. You mentioned at the very end that this volume picture corresponds to the leading term in the expansion. And could you comment on how much of the beauty and the symmetry of the answer comes from the fact that it's a leading term? And if you were to consider terms afterwards, there would be extra complexity coming in?
Oh, so 2 things. First, the symmetry is actually there separately for each term in the expansion. Okay, so there is a well-defined symmetry. It's there in leading, the subleading. It's there in all of them. That literally the picture of literally that volume, literally that shape, is true literally for a cousin of the theory of gluons that has maximal supersymmetry. Okay, so it is not the real world, but it is the real world to the leading order of approximation. So what that means is that the real world to leading order of approximation has a magical symmetry. It has some magical properties. Literally, it has some. I didn't have a chance to describe it. It has an infinite amount of symmetry that could have been spotted by people 60 years ago. It just wasn't. It wasn't spotted until 8 years ago. Okay, but it really has sort of some magical features that again, there are all these clues lying there under our noses that there's something going on. And in the real world, that thing is probably, that symmetry is, in the way we understand it, is definitely messed up by the subleading corrections. But that's not necessarily that's not necessarily good or bad for this picture. What we don't know is what, if there is one, and if there is, what it is, analogous kind of geometric understanding for not just the leading piece in the real world, but the subleading, but all the pieces. And in fact, some even better understanding of the whole answer that doesn't force us to divide it up into these little pieces that we add up.
Before we get to the blue, we're going to do a couple from the web, from our live stream audience. So Anne?
So we have 2 questions from YouTube. The first one is, what do you think of James Gates's supersymmetry research suggesting error-correcting codes are embedded in the fabric of the universe?
Oh, yeah, I know Jim Gates very well. It's very, very interesting work. Yeah, I mean, I don't know. I don't know. I don't know a lot of. I mean, I'm not an expert in the subject. Okay. Yeah.
Who is it from?
Fabric of the universe is pretty heavy stuff. So, the
person did not give their name. Goddard's Journal from Maryland.
That's okay.
The next question.
But it is fascinating stuff. Yeah.
does the polyhedron have to conform to certain relevant or familiar symmetry group properties?
No. I mean, in other words, at least so far in this picture, it doesn't matter if the shape, it doesn't matter if it's like a dodecahedron shaped or something like that. It doesn't matter if you give a particularly special looking version of these shapes. What matters more is the sort of network of relationships between the vertices and the edges and the faces and how they're all sort of tied together. That's much, much more important.
So we'll go to our blue.
I'm Joseph Powers, and I'm not a member. And while I appreciate the color-charged theme of the microphones tonight, I wondered, sort of at the end of your talk, when you're talking about these pictures that are much simpler than the Feynman diagram, in my mind, I'm imagining testing these theories to find out what is the truth. And it seems to me that while the strong force is what you measure at the Large Hadron Collider, it should be more fruitful to look at places where you know the standard model isn't working, like flavor oscillation and the neutrino mass. And so I'm wondering, how would you draw a diagram for various predictions for that sort of thing?
Yeah, well, so first let me make just a few comments about that. First, the whole nature, I tried to emphasize it, but I'll say it again. The whole nature of what we're trying to do is not to change anything. We don't want to change anything now. I mean, right now we have a pretty modest goal, which might still take the rest of our lives. But it's still a fairly modest goal to try to reformulate standard physics in a different language, where we don't rely on this notion of space-time and quantum mechanics. We're not trying to change it. We're just trying to find a different starting point that will give us identical results. Okay? And in fact, the very modesty is what's giving us a way of knowing that we're not screwing up. You know, we're not just speculating and wondering. Whatever we do, we have a way of checking whether it's right by either matching it to standard ways of doing the calculation, or often that's not available, but you can still check whether the results conform to space-time and quantum mechanics. Okay, you can check whether they conform to the rules. So we're not trying to change anything, and it's not a question of whether is Feynman diagrams more correct or this is correct. By design, they should give us exactly the same answer as Feynman diagrams. Now, you could say, why the hell are we doing it? Well, A, there's the practical thing that the Feynman diagrams are very hard to calculate. But B is for all the philosophical reasons I said in the first part of the talk, that this is a safe way or a beginning way to dislodge our addiction to these concepts that we suspect we have to get rid of eventually. But to your question about neutrino oscillations and other things like that, first, yes, it's true, neutrino oscillations go beyond the standard model. They go beyond the standard model in a very, very mild way. Okay, so a competent second month graduate student in this field will know how to change the standard model in a very small way in order to accommodate neutrino masses. So it's not some big, it's very, very easy to do. If you ask, it's true, it's officially beyond the standard model, but only in a rather minor way. It's a very interesting phenomenon. We should measure them and learn everything we can about them. It's part of nature, but it's not some dramatic extension of the standard model in any way. Now you could ask, how do we see any of those things from this other kind of point of view? That's a very interesting question. There's a lot of both theoretical technology that needs to develop in order to figure out how to apply all these ideas to the case. Everything I talked about is some idealistic situations where the particles don't have a mass. They're the strong interactions, but they don't have all the complexities that we'd have if you dealt with top quarks or even electrons interacting with photons. Is actually a slightly harder problem than the one that we're talking about. So there's a lot that needs to be developed. But you could imagine as a goal to try to figure out some underlying principles, be it geometric, be it, as time goes on, we see that it's not even geometry so much, it's something really fundamentally combinatorial, which sits underneath everything. But be it geometric or combinatorial or whatever it is there something that actually works to describe everything in what we see in the real world around us? That's a very concrete goal. We're very far from that. We're very, very far from that, but we're taking first steps towards it.
Last question, red microphone.
Hi there, yes, Brad Cook, and I'm not a member. And I'd like to thank you again for a terrific talk. And I'm afraid what I have to say, though, may seem something like a complaint, because you did a really good job. You did a really good job in conveying, to me at least, the relationship of the amplitude-hedron to particle physics. What I didn't get from the talk, though, was how it relates to gravity.
Well, it's good, there's a good reason you didn't get it from the talk, because we don't know. I wasn't trying to hide that fact. Yeah, it's well, I mean, that's a little glib. It's a little glib, but that's basically true. Yeah, I could
make sure to ask.
Well, so let me be slightly less glib. Okay, So just for some observational facts about the data again, just the theoretical data. So if you're a student learning how to do these calculations, you love the answers you get from very simple toy theories that are at the beginning of all the textbooks where the particles don't have any spin. Okay, they're called scalar theories, but never mind. Those are things that you can do even with 4 or 5 or 6 points. No problem. You can impress your professor, but they're not impressed anyway. Okay? Then the next most complicated ones is when the particles have spin 1. They're like gluons, right? And that's the one where, 2 to 2 you can do in a problem set. 2 to 3 is 50 pages, very hard. Then the next then after that is gravity, which is spin 2. And then even just 2 to 2 for gravity is like 1,000 terms. Complete nightmare, okay? Just totally insane. So usual point of view, textbook picture, Feynman diagrams. You order complexity. Low spin is simplest. Gluons in the middle are pretty complicated. Gravity, ridiculous. Okay. Now, at this moment in time, what we know about the actual final answer, how do you think the simplicity is organized? It's exactly backwards. Okay? Gravity has the simplest possible final answer. Gluons have intermediate, and the worst and most complicated and horrible ones are the ones that involve the scalar. So there's lots of evidence that the answer in gravity is somehow has the most remarkable structure in it. Furthermore, the answer in gravity is a thing that's naturally lifted into the sort of first avatar of string theory that people were excited about in the 1980s, and even, well, they're still excited about today, but where it was born. And there's lots of mysteries left over that we still don't understand. There's clearly an ocean of structure associated, of magical theoretical structure associated with gravity, much of what is still hidden. So why do we care so much about gluons in the middle, right? So what I just told you seems to be some intermediate objects. Well, 2 reasons. One is the sort of practical one that experimentalists care about them. But the other one is a little more interesting, is that something that the string theorists really discovered is that, to begin with, but which has been seen in a way that kind of removes its stringy origin, and you can see it more directly, kind of as an intrinsic statement, is that in a very concrete sense, if you know the answer for gluons, you can kind of square it and get the answer for gravitons. So there's a very interesting relationship, completely hidden. I mean, if you stare at the rules for general relativity or the rules for gravity and the rules for gluons, this fact is completely unobvious. The only thing that would make you think there's a relationship is just that the gluons have spin 1 and gravitons have spin 2. So in the absolute dumbest sense, you might think that 2 gluons going like that would kind of look like a graviton, which is, of course, just super lame because just move them a little and they don't anymore, right? So that's not, that can't be it. But that's the beginning of what gives it a chance of working, okay? And that relationship has actually been seen, and there's something deep and important about it. So it's actually the way string theory likes to think about gravity. It's fundamentally a squaring what you get from gluons. So for instance, if you've seen any NOVA specials, you'll know that gravity is associated with little closed strings like this. Gluons are associated with little open strings like this. Well, but a little closed string is like 2 closed strings glued together like that, and so on. Okay, so that's why, in some sense, it seems like gluons might be the most primitive, sort of basic object that then get transformed into gravity in some way. On the other hand, there is something against that, which is just that that the gravity answers directly have even more structure in them than you would expect. So I'm giving you no clear answer to your question, but I can tell you we don't know anything like an amplitude, not even close for gravity, never mind for strings. But there's lots of suggestive links between things that have been seen in string theory, the squaring relations or other things that says that if we're mucking around the right neighborhood for gluons, we can't be too far from saying something interesting for gravitons.
Well, thank you so much.
Wow. Oh, sure.
So before you go, we have two gifts for you. One is a framed copy of the announcement of your talk,
That's
signed
so
by
cool. Thank
the
you.
members of the General Committee on behalf of all the membership.
Thank you.
And the other is your signed copy of Volume 1 of the PSW Bulletin.
Really?
published in
Volume 1, eh?
1871, where
That's
you can
awesome.
you can learn many things, among which are the original members and why they should have called it PSW Science
All right.
instead of what they did call it.
Thank you. Thank you very
So,
much.
Thank you.
Oh, sure, yeah, I'll have to. Thanks.
While I'm handing out signed volumes, I think Emily is in the audience somewhere, and she can come up and get a signed volume too. Now, before we go, there are just a few housekeeping announcements. First and foremost, thank you to all of our members, sponsors, and supporters. PSW depends on them, and if you're not a member, please join. If you want to join, it's pretty easy. You can just go to the PSW homepage, which for the time being looks like this, but pretty soon, thanks to our web overseer, Jared McQueen, it's going to look a lot nicer. But you go to our webpage, and there's a little button that says membership, and you push that button,
No, it's fine, it's fine. This is
and
really
you'll
cool.
get a membership application. Surprising, eh? And you go fill it out and go down to the bottom and push the submit sign button, and that's not what will come up. What will come up is the payment page. A payment page will come up, and you can pay with a regular credit card. Don't be confused by the PayPal logos that appear on the page. PayPal is just our bank clearing service for credit card payments. Just look for your usual credit card logo and fill out the form and pay your dues.
We had record
And
numbers, online
that's all there is to it, really.
great.
And there's no IQ test in any way. If there were one, anybody who came to hear this lecture would pass. And if you are a member and you haven't paid your dues, please pay your dues. Our next lecture and the 2,385th meeting will be on Friday, December 15th, right here in the Powell Auditorium. It will be the last lecture of 2017. The speaker will be Douglas Smith of Duke University, and he will be speaking on the topic of metamaterials, which can be used to make cloaking devices and perfect lenses, among other things. Doug is the leader in the field of nanostructured materials that have properties that are impossible for conventional materials. Among these are unique optical properties of lossless refraction, frozen light, and cloaking devices. Technologies based on such metamaterials are going to advance many other areas of science and enable magical materials and devices in the marketplace. The spring 2018 lecture series is under construction. It's almost completed. As of now, our speaker for the President's lecture on January 5th will be Margaret Lehman, who is the Dean of the Scripps Institution of Oceanography and the Vice Chancellor for Marine Sciences at University of California, San Diego. She'll be speaking on some recent very interesting developments in oceanography and about some of the unique institutional facilities at SIO that make these advances possible. On January 19th, we have a young and very increasingly important scientist, Aviv Regev from MIT. She's a Howard Hughes medical investigator, and she has an appointment at the Broad. She's going to talk on the catalog and diversity of cells. She is a fantastic young researcher who's developed methods to do whole genome expression profiling on single cells and to do it on large numbers of cells in parallel. Her work is rewriting our understanding of how many different kinds of cells there really are and how much a given type of cell varies in its gene expression profiles and other characteristics. It's very interesting work, well worth hearing about. On Feb 9th, we have Christopher Ralston from GWU on faking cultural heritage, the Israeli forgery trial in particular. Chris is a brilliant linguist, capable of rubbing a few feathers with the facts. He likely will be telling us about the trade in antiquities and in forgeries, including how we detect them, and about the ways in which antiquities frauds impact scholarship, and when they have religious significance, communities of believers. On February 23rd, we have Thomas Zuberchin of NASA, and he will be speaking on a topic that we don't know yet, but probably has something to do with space. Andrew Knoll of Harvard will be speaking on life on Earth, the deep history. It will be interesting to see if he found any self-replicating RNA enzymes, for those of you who were at the previous lecture. But he will certainly be speaking on identifying and studying fossils that constitute the remains of the earliest living things so far detected. It's a subtle and challenging endeavor, and I'm sure you'll find it interesting to learn about these far distant relatives, or at least these living creatures who might or might not be far distant relatives of ours, and whether and where we might find the residua of even earlier forms of life on our planet, and what will it tell us about finding life or signs of life in other places off of Earth. On April 6th, we have Jordi Puig-Suari from Cal Poly, and he'll be talking about CubeStats. And he should be able to tell us a lot about them since he is one of the inventors of them. And then finally on May 18th, skipping the 2 dates that haven't been scheduled as yet, we will be having a Cassini special. I'm sure many of you know a lot about Cassini, and it has met its end in the gravitational and exotic and very horrible conditions of Saturn, which it plunged into not too long ago. So we're working hard to make this year's Joseph Henry Lecture a set of several presentations on Cassini by scientists who brought this space vehicle into being, got it to Saturn, oversaw its navigational gymnastics, and took fantastic pictures of the planet itself, its rings and moons, and have interpreted the vast, rich ocean of data that Cassini sent back to us during its many years inhabiting the Saturnian system. So with that, I will entertain a motion to adjourn the meeting to the social hour, which usually ends at 10:30, but I think we'll extend it tonight to 10:40. Do I have a motion by a member? Eric. Do I have a second? Carl. All members in favor of adjourning to the social hour? All members opposed? We are adjourned to the social hour.